Okay, thank you very much, Albert. I'd like to introduce next Jorge Ocon, who will present an architecture for autonomous rovers on future planetary missions.
Presentation. So good afternoon. My name is Jorge Ocon. I work for the Space Segment Business Unit at GMV in Madrid. And this presentation is about an architecture for autonomous rovers that we are working with, and we have been working for in many different projects during the last years. So this is the index of the presentation. First, we will discuss the mission and system drivers for autonomous surface rovers, and a little bit about the background, the projects in which we have been working, and the concepts and notions about autonomy. Then we will discuss our solution for onboard autonomy, and also a solution we have been developing for long traverse autonomous navigation in the frame of Spartan. Finally, conclusions and questions. So the main difference between a planetary rover mission and other deep space missions is the hard interaction of the rover with the surface and the uncertainties related to the surface. We also don't know what will be the weather conditions and what will be the energy that can be obtained by the solar panels, and also the energy that it will take to perform the different operations of the rover. So all these uncertainties need to be handled by the rover, and it requires also autonomous long-range navigation capabilities so that we can autonomously traverse from one position to another, which also requires long-term mapping, path planning, motion control, and adaptive executions. So we need fast driving capabilities combined to opportunistic sense abilities in order to detect specific events that can be interesting in order to gather signs, get samples, or take images. Moreover, we need to perform complex sample fetching operations, and overall, we need to guarantee the reliability and the safety of the mission for a successful mission completion. So all this affects the way that the rover is to be commanded. If we look at the different autonomy levels for commanding in the European standards, we find 4 different levels. The first one, E1, is the traditional way of sending a telecommand that is to be executed immediately on board. E2, time-tagged telecommands that are executed at designated times. E3, that is based on events. Once an event is detected on board, it is executed. And E4, that is based on high-level goals commanding. E2 is not a good strategy because of the latency and the lack of communications, because it leads to a very inefficient use of the resources of the rover, because we need to be very conservative. We don't know at the time in which the command will be executed what will be the circumstances, and therefore we have to be very conservative. A much better strategy is to use E3, in which we can command nominal procedures to be executed and contingency procedures to be executed when unexpected events occur. But the best way to handle, or what could be the optimal way to to deal or to command this type of rovers is to use E4, in which we will have the possibility to command via high-level goals. By high-level goals, we mean, for instance, to explore a given area or to take an image at a distant position or to pick an example, so that we can, at the beginning of a sol, send these 3 goals and let the rover do the job. But for this, we need a planner. We need an onboard planner to decompose these high-level goals into lower-level actions to be executed. So during the last years, we have been working with ESA and with the European Union in different projects related to autonomy and also to visual navigation, mainly GOCHA and GOAC, oriented to the consecution of a goal-oriented autonomous controller, and Spartan, Compass, and Sextant regarding long traverse navigation. Also the RAT, in which we built a platform to be used at the testbed. And right now we are working in 2 different projects, 2 different European projects, ERGO and SROCOS. ERGO aimed to goal-oriented autonomous controlling again, but this time with a much wider scope. And SROCOS oriented to the consecution of a robotic control operating system. We are leading both projects with several partners all over Europe. And we also have tested these technologies under Martian analog conditions in the Lucid project in Tenerife and GOCHA, including Spartan, in the facilities we have in Colmenar Viejo, very close to Madrid. Furthermore, we are going to test the ERGO technologies in November this year in Morocco. So the requirements for the solution that we have developed are to be able to be commanded in E1 to E4, to allow for opportunistic signs gathering, to have deliberative and reactive features that work in a harmonized way, and to allow for the execution of the plan interleaved with the planning. I mean, to be able to dynamically change the plan when the conditions are such that we have a new goal, either because we receive it by ground or because the plan is not being matched and we have to replan in order to accomplish our goals. The system is able to perform continuous operations and uncertainty, and we have taken into account also the safety circumstances of space with a robust FDIR and the modularity and scalability of the systems. The plans that are built are based on flexible time boundaries, so that there's no need to modify the plan as soon as these flexible boundaries are matched. So this is a sketch of the architecture. You can see that there are two different parts. First is an agent that controls the functional layer that is in charge of interfacing with the hardware. So the agent is made by what we call reactors, that are more or less components that fulfill a given interface. And these reactors have a hierarchy. On top of the hierarchy, we have a ground control interface that handles telemetry and telecommands, and also the autonomy level. The autonomy level is the variable that controls the way of commanding. So the interesting thing here is that when the system is commanded via high-level goals, they grow through this planetary mission planet reactor that decomposes them into a feasible plan. And the planet reactor uses the interface with the functional layer, these command dispatcher reactors, in order to control the execution of the plan, to monitor it, and to check that the plan is being accomplished. If the plan is not being accomplished, if there's a violation of any constraint, then the system replans automatically and tries to fulfill the goals that it has to perform. Moreover, there's a scientific detection component that is able to detect scientific events and then inject goals to the mission planner reactor, so that, for instance, we can request the planner to change the plan in order to gather signs, to take a picture on a different position. So there's a clear barrier between the agent and the functional layer, which allows us to test it using the same agent, to test it with simulators or sometimes with even different platforms. And we have also an FDR component that is aimed to control that no matter what happens, what the planner reactor does, it will not harm the robot. The robot will always be safe. If the mission planner reactor is not able to fulfill its goals, it will automatically degrade the level of autonomy, so that we will go to E3. And in E3, there's no deliberation, and the system becomes a traditional one. The level of autonomy can also be commanded from ground. So, to make you an idea of how this works, the planner builds a plan, and it controls its execution via the command dispatchers that interface with the functional layer. And as time goes by, it checks that the plan is matched. And if it's not, it replans. If it finally is not able to replan, it will raise a signal, and it will lower automatically the autonomy level. The planner is based on a problem and a domain that are defined using planning languages, so that we can say that the system is model-based, because the model of the plan has a really important influence on the way that the planner works. So the other technology that we wanted to discuss is the long traverse navigation, developed in the frame of Spartan. We have been developing a system for long traverse autonomous navigation for rovers, and it has into account three important requirements: the fast execution, the high accuracy of the localization system, and the rover safety. It is based on computer vision, and we have chosen this because it guarantees passive mode of operation, less power consumption, simple hardware, and a small form factor, and also very high accuracy. These techniques are computationally demanding, which is a challenging problem, and for that we use a combination of the CPU with an FPGA, so that the higher floating point accuracy of the CPU is used in combination with the FPGA. The algorithms are chosen in such a way that the work can be performed in parallel between the CPU and the FPGA, and those operations that are floating point operations are performed by the normal CPU. Meanwhile, the FPGA performs those operations that can be performed without the need of floating point. So that the 97% of the total computations are performed by the FPGA. This is, at the end, becomes a much more efficient system, and this logic has been tested in FPGAs that are equivalent in size of performance to the next generation of European space-grade FPGA devices. The software elements have been tested in Leon processors, and therefore it is already a viable solution for space navigation. We have conducted field tests in Tenerife and also in Colmenar, even during the night. And we have also tested real sequences from Mars-Salanogate terrains in the Atacama and Devon Island. So this is a field test that we have been doing. This was taken last week. I have to apologize because at some point the camera, we moved the camera because the rover gets out of the area covered. So we are injecting here a telecommand to take an image at a given point. And the rover goes, well, the planner builds the plan. There's a path planning. See that we had to move the camera at some point, but nevertheless, the rover reaches the point, and you will see the PTO moving at some point when we take the image. Yeah. Then we inject another TCE4 telecommand so that the plan is being modified. We go to a second point. And meanwhile, we are going to this point, we inject another telecommand so that the plan is modified dynamically, but that does not affect the rover actions. It is going to the second point, and now it's going to the third point in order to finish the plan. So this test was aimed to check that we are able to inject and change dynamically the plan. There are other tests, as for instance, we are able to send 3 telecommands in a row so that it makes the plan for the 3 telecommands in just a single shot, and we don't need to replan, as we would do if we were commanding it on Mars. And other tests include injecting errors and checking that the plan is done again. So, as a conclusion, future exploration missions will require high levels of autonomy, currently beyond the state of the art, and this affects many functionalities of the rover: mission planning, long traverse autonomous navigation, path planning, hazard avoidance, trajectory control, and also verification and validation. We have been developing for ESA and EU solutions for onboard autonomy and also for long traverse navigations. These technologies are being tested currently in analog field tests. These technologies are also available to guarantee mass sample return success. It enables technologies for better scientific return, and the level of reliability is being tested currently, and mission reliability is guaranteed by the capability to handle all possible levels of autonomy, to be commanded from ground, and also to have a scientific agents able to send dynamically new goals and change the plan for opportunistic science. Finally, we have a component of visual navigation for long traverse navigation that is a viable method for space and has other advantages over LiDAR, such passive mode, simple hardware, small form factor, and low power consumption. So that's it.
Thanks,
we have yet another video, but it's 5 minutes, and I don't think
we have time for that
no.
at the moment. Thank you.
Okay.